Well, so welcome to lecture 8 of our CS2 classes. And yeah, in day before yesterday's lecture, we started off with reinsurance, right? And we saw that there are two different types of insurance, proportional and non-proportional. And again, what we try to figure out is the mean of the claims distribution and the variance of the claims distribution. So as to be able to, do some prediction analysis for this year claims, which we do not yet know, and have some prior reserves in place from what we expect the claims to be like, so as to, not be dealt with an unforeseen risk, which could lead to a bigger loss. So it's better to be prepared than to be not prepared, because anyways the risk is there, underlying risk is always going to be there, and loss, if it is to happen, it will happen always. So again, if something we can do to predict it, that's well and good. So again, in yesterday's lecture, we had a look at how to figure out the expectation, variance, and the moment generating function for non-proportional case, which is the excess in loss case. So we had a closer look at the distribution of ceding companies' claims and reinsurance companies' claims. And then here we assumed that, everything was known to the reinsurer, but then we also took into consideration the scenario of where a reinsurance company might not be aware of any claims, which doesn't have to do anything with them. So what we looked at was the conditional distribution for the reinsurer's claim amounts. And we got a nice PDF, which was in terms of X. So again, we don't have to, shuffle up a bit here and there. It's just right there. Just substitute these values and we'll get the answer for our PDF and CDF if at all we need it. And similarly, we also devised and derived RV through the expectation of W, not only in terms of W, in terms of X, as well as in terms of Z. And the way we defined Z was X minus N. And I guess the main important thing to remember here is that M is a constant and many things become easier just because M is a constant. And then we just had a look at, an example, and we stopped right here. We said we're going to have a look today at how do we even solve this integral. So I had a couple of, answers from you guys, which said that if I substitute the f of x here, it would become a bit more complicated, right? But let us try to do something, if at all there is that we can, to make this not complicated. So did you guys have a thought about what could I do here? So let us say, normal distribution isn't that complicated, I would say. And again, I would say, not that it's necessary, but just for you guys to be comfortable enough with the integration, I want us to, solve this integral right here together. So let us maybe try to solve this integral here. So, okay, if I were to write now my f of x here, what will I be writing? So I'll just rewrite this integration from 550 till infinity x. And I know what is my f of x here. My f of x follows normal distribution with mean 500 and variance 400. So if I were to write my PDF of the normal distribution for this scenario, let us for now, just say that this is my mu and this is my sigma square. And I'll just write u and sigma here, and then we'll see, if there is something that we can do. And let me just maybe make this n as well. So I'm just going to, make me not write a lot. And yeah, let's see what happens. So if I write my x here, can someone dictate me what should I write here? So I want the normal distributions PDF. So I think it's just gonna be as it is from the book. So if you go to page number 11 in your table booklets, you will see this formula right there. and we have e raised to minus a half of x minus u upon sigma the whole square. And again, I shouldn't be forgetting my dx here. Okay. So now if I want to solve this integral right here, what would you guys suggest me to do? Anyone? Any suggestions? What can I do? I have a x here. Yes. Anyone? What kind of a method I can use here to figure out this integral?
Can we take x minus mu upon sigma is equal to t, like some variable, and then substitute?
Let us try and we can see what happens, right? Okay, so let's try. So what I'm gonna do now is, what did you say? I'll write my x minus u upon sigma as t.
Yes, ma'am.
Okay. So now what should I again be doing is d here and d there as well. So I'll have d of x minus u upon sigma equal to t. So what will I have here? So basically what will my dt be equal to?
Dx upon sigma.
Dx upon sigma, right? So basically dx and sigma inverse, right? Okay. So now if I were to substitute everything in here, let us see what happens. So I have an Yeah, so I'm back again. Okay, so what I'm gonna do now is I'll just rewrite my x in terms of t here. So instead of x, I have written sigma t plus u mu basically. And now this will be as it is in the denominator. So I have sigma square root of 2 pi and e raised to a half of minus a half of. So I know that this is just t now. So this will be t square. And instead of dx, I'll write dt times sigma. So I have sigma and dt. And again, I see that I can cancel up this sigma and that sigma, right? Now, what do you guys think I should be doing?
And don't we have to change the integration limits, or it will
Yeah,
remain same?
well, yeah, perfect. Thank you very much. I was actually waiting for someone to catch on that. So again, yes, we will have to change the limits, right? Because I have x minus mu upon sigma equal to t. So let us say if my x is m, what will my t be? My t will be sigma. It will be sigma inverse of m minus mu, right? And if my x is, let's say, infinity, my t will again be just infinite, right? So I just have to change the lower limit for now. Perfect. So now what I can do is, maybe let us, try to substitute the values of sigma and mu here as well as m here. So we know that my sigma is 20, my mu is 500, and my m is 550. So what do you guys think I should be writing here as the lower limit instead of m? Anyone? What should be my lower limit? Can you figure out? Sigma times m minus mu. Sorry, sigma inverse times m minus mu.
2.5.
Exactly right. So this will be 2.5. And maybe we can highlight that because this is very important. Did it highlight? And then it will just, okay. Yeah. Okay, it doesn't work on black. Fine. So, okay. So now what should I be doing next? What should I do next? Anyone? Now I have all of my limits changed as well.
Take the constants outside and substitute the value of mu and sigma.
So which constants can I take outside?
1 upon under root 2 pi.
1 upon under root 2 pi. Okay. So I take 1 upon under root 2 pi outside. Then
Substitute the values of mu and sigma in the integration.
so what's my sigma? It's 20t plus 500 e raised to minus a half of t square dt. Is that it?
Yes.
Now what should I do?
Split the integration. So the first part will follow the u into v rule, and the second we can just.
Let us see. So if I were to just split these integrals, I'll have 20t times e raised to minus a half of e square dt plus mu will also come out, right? Because it is just another constant. So 500 upon square root of 2 pi integration from 2.5 to infinity and just this. Okay, so what do you think I should be doing here? Even 20 can come out as well, right? Or is there any more efficient manner in which we can solve this? Okay, let us try to solve this integral first. This seems a bit easier to me. What do you guys think of this integral? Anyone?
Ma'am, can I tell for the first integral first?
Yeah, sure.
So what I thought was we could use the substitution method, and instead of taking the 20 outside, we would take the 10 outside and keep the 2 inside. So we would substitute t square equal to some variable, and therefore then, for example, t square would be equal to v. So then taking the derivative, it would be 2t dt would be equal to dv. So we have 2t and dt as well.
Exactly. So that is exactly what we are going to do. And again, you are going to do. I'm not going to solve it on the board because the board has ended here. But again, if anyone cannot solve this, just let me know. So again, I'll just write that we're going to use here substitution, where I can just equate my t square to be something, let's say p here, and I know that my 2t dt will be dp, right? So, and then I'll just solve it. And I guess for this, what do you guys think? What can happen to this? What should be happening to this?
I'm in the PDF of standard normal distribution.
Exactly right. It is just, so I can take this square root 2 pi inside and it will be the PDF of standard normal. So basically normal 0, 1. And I guess you all are aware of how to solve this. So you have got this, and we already got this yesterday. So we have all the parts, right? I mean, it was complicated, I know, but again, now I can easily skip the proof because I guess we have already, done it. And let me just try to show you guys the theory behind, or basically the simple formula that you can use always to solve such kind of integrals. So not always you guys will have to go through all of this process. So yeah, it's easier if you have a look at, let's say, page number 18. So can you all open page number 18 in your table booklets? You will see the truncated moments, right? And those are written for normal distribution as well as the log normal distribution. So let me just have a new share. And can you all see the book? I guess yes. So Again, I'm not going to, write all of this stuff down. It's just going to take more time and gadamajuri basically. So, okay. So I'll just go through this, very fast and let me know if you guys have any doubts, because at the end, what you will have to do is just substitute this UL here and get these formulas and you will have your answers. And we'll do sums as well today, which will involve you using these formulas so that you get a hang of it once at least. So, okay, so let us start with normal distribution. And again, we have these, curated formulas because we know that this come up usually a lot more often than we would expect it to. And we don't want us to solve this stuff again and again. And yeah, it's basically just some mathematics. And if we can have a concrete formula, it's well and good. Let's just use it directly and apply our brains somewhere else where it actually matters. So, okay, I have my X, which will usually be the claims, and it follows normal distribution with mean mu and variance sigma square. And just like in the previous situation, we would have some sort of an integral always, which we are to solve. And we have x f of x, but the only thing stopping us from equating this to a mean is that we have a lower limit and an upper limit, which is not 0 and infinity at the same time. So it could either be 0 here, but not infinity here, or infinity here and not 0 down there. So, okay. So this is the formula that you get. So if you have a closer look again here, you see this is just the mean of the normal distribution. And this is just the sigma of normal distribution, right? For the x that we have. But again, here we have defined some new integrals, some new integers, u dash and l dash. So whenever I'm talking about l, yeah, so I guess internet is acting up a bit, but again, it's back again. So yeah, I guess what I was saying is we have our u prime and we have our l prime. So if you have a closer look here, this is phi, which is the CDF of the standard normal, and this is phi again, but the PDF of the standard normal distribution. So what the simple formula is just mean mu and the phi of u prime minus the phi of L prime minus sigma psi of u prime minus the psi of L prime. So I hope that's clear. And again, yeah, they have said that this result is given in the page number 18 of your table booklets. But I would say, let us just go through its proof once. So we actually just solved that integral, and that is the same thing that even they are going to do here. But again, I'll just, walk you guys through it. So we have integration from L to U x f of x dx to start with. The very first thing, you substitute the value of f of x right here, and you have it. And then what you're going to do is you now equate x. So as yeah. So the way we did it previously was exactly the way they are doing it here. And what they're doing is basically they're equating x minus mu upon sigma to z. All right, so now instead of dx, we have dz, and you see the sigma is gone because it gets cancelled out from here. And just to remind ourselves, so we get dx upon sigma equals to dz. So my dx will be just sigma times dz. And if you keep this sigma here, and if you keep a sigma here, it will get cancelled out. So not much to worry about there. And again, instead of x, you have now mu plus sigma z, and again the limits. So for each x, so basically if your x was L, we know that L minus mu upon sigma is what we define the L prime as, and u minus mu upon sigma is how we define our u prime as. So again, not anything fishy going on there as well. And as we tried to split it up, even they did the same. So you have mu here, and then you only get the PDF of standard normal here. And again, you have sigma here and something with a Z, and again, the PDF of standard normal here. So that's what they have written here. And again, this would just be, because we have L prime and U prime, it would just be the value of standard normal lying in between U prime and L prime. So yeah, we can ignore that. And let us see what they have done next about the next integral. Okay, so now we have something up here. And what they have done is, again, they sort of did the same thing. And they've written this as it is. And if you just ignore this part for a while, let's just walk ourselves through this. We have this thing and we have just substituted phi. So basically, if I want to figure out this, and what I'm saying is, let us say this is how my standard normal distribution looks like. I have my mean here, which is 0, and my variance is 1. And I'm trying to figure out the area that there is in between U prime and L prime. And again, this did not lie on the either side of 0. That is just for demonstration purposes. And if I want to figure out the area that lies underneath this part of the curve, what I can do is I can take the whole area, this, and subtract from it the rest of the part. So if this is my A and this is my B, I know I can define my A as the phi of U prime, right? And I can define my B as the phi of L prime. So again, this is just, the probability that my X will take a value less than or equal to U prime. And the same thing here as well. And what you're left with is this part, which is what we concern ourselves with right here. And again, what they have done here is just replaced U prime with U minus mu upon sigma and L prime with L minus mu upon sigma. Does this part make sense to everyone? I mean, this is just again, repeating the same thing that we all just did. Does anyone have any doubts with this? Yes or no?
No doubt, ma'am.
Okay. What about others? Okay. So I'm assuming that it's a no for everyone else as well. Okay. So now let's see what happens in the next case. So what they do is they again use the substitution method and they get the same thing here. So they haven't clearly carried out the substitution here. But again, if you try to solve for it, you will get the same thing. Or maybe let us just solve it right now. Okay. So what we have here is Z 1 upon blah, 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 and Z square, right? So what do you guys think I should be doing to go from here to there? Yeah. What should I be doing? So this is basically where my board was ending in the previous slide that we just did. Anyone? So, does anyone remember what did Vanshita say in the previous slide about solving such integral?
We can take z square equal to another variable and then
Right. Who was that speaking?
me, ma'am.
Me, right? Yeah. Okay. So again, let me just take z square as t for now. So what will I have? 2z dz being equal to dt, right? So again, what should I be doing now? Instead of z, what should I write? Or let's just leave it as z because we have a z here as well. 1 upon square root of 2. So this is a z, okay? 2 pi e raised to minus a half and z square will just be t. And instead of dz, I'll have dt upon 2z. And this z and that z will just cancel each other out. And what do we have now? Did I miss something?
Ma'am, the 1 upon 2 into root 2 pi will come outside, and the integration of e raised to minus half t will be just e raised to minus half t upon half, minus half.
Exactly, right? So again, I can just write 1 upon square root 2 pi outside and e raised to minus a half of t upon 2. Dt is what we are trying to integrate. And using the usual rules of integration, what will we get? We'll get e raised to minus a half of t as it is. And then we'll have to differentiate this by right here. So again, this 2, if we just take it as it is right here, we'll get minus 2 here in the numerator and L prime, U prime. And this 2 and 2 will get cancelled, minus will be left. And again, this constant, so I can just take it inside the way they have taken over here. And remember the minus that we got here. So minus of e raised to minus of half t. And again, I would just, replace t with z squared upon square root of 2 pi. Does this make sense? Does anyone have any doubts with this?
No, ma'am.
What about others? Andrea, Isha, Savri?
No, ma'am.
So if you want me to do it again, I can actually go over it again as well.
Ma'am, can you please go over it again once?
Okay, yeah. So where exactly are you confused, Isha? I mean, where should I start from?
Ma'am, the power had gone out again, so I'd gotten disconnected.
Okay. So I'll just tell you what happened. Actually, the power was cut off from my side as well. So again, we started off with this integral right here. And what we did, we assumed this z square to be t. So we assumed our z square to be t. And then if you just take differentiation, you get 2z dz, which will be equal to dt here. And now you substitute this thing in this integral right here. And what you get is, instead of, so you keep this z here because we know that we have a 2z here as well. So this z and this z will cancel out eventually. And we'll have 1 upon square root 2 pi here, e raised to minus a half of t, because we equated z square to t, and dt upon 2z for replacement of dz. So that's it. And then this z and that z cancels as we anticipated. So we have L prime, U prime here, e raised to minus a half of t upon 2 here. And we take this outside as the constant. And now we just solve this as the regular integration, and this is what you get. Does this make sense? So
Yes,
again, the way we solve, this is just e raised to minus of this thing. So e raised to minus of half of t, and this 2 is as it is, and this minus 2 is the derivative of this in the denominator, which will eventually, go here in the numerator. And yeah, that's this. It's exactly that you get here with the sigma. Perfect. And then again, we know that this is just the PDF of the normal distribution with a minus sign. So see, this plus has now converted to a minus here, and which is why you still have phi of u prime minus the phi of L prime. Otherwise, it would have been plus of phi of L prime minus phi of u prime because of the minus here. But that's the same because the PDF is just this. The PDF does not have the minus, right? So you have to be mindful of that as well. And again, that's it. So you again resubstitute for u prime and L prime here. And this is your final formula, which is written in a very clear and concise manner as this thing right here. So yeah, that's all there is to this formulas. And again, you don't have to, go through all of these things. Yeah, and I'm assuming that you guys are aware of these things. Maybe we can just draw a little something. So we have phi of minus infinity. How do you guys think I can represent this? So how do you guys think I can represent this on the graph here? Anyone? What is the probability that the value of x will be infinity in this case? I couldn't hear you well.
The probability at infinity, right?
What? What did you say?
Can you repeat your question?
It's written over there, right? The thing that I have written, phi of minus infinity. How can I represent that on the graph which I have drawn? So the mean is 0 on the graph. Can you see that? It's in the red.
Yes.
Yeah. So what I'm asking is, how can I write this thing? Sorry, how can I draw this thing, this probability on the graph here?
so that will be the same as 1 minus phi of infinity, right?
1 minus
Phi of infinity.
Do you mean this?
Yeah.
And what does this represent in terms of probability? What should I put here?
Infinity only.
So should I put a less than symbol here, greater than symbol
Yeah,
here,
less
or
than,
equal
less
to?
than.
Less than.
Less than, okay. So again, just try to remember what I asked. Okay, so let us try to write this in terms of x. What should I write here? Less than, greater than, or equal to?
Ma'am, actually, I have a doubt. It's a bit silly one, but still.
No doubt is silly.
Can you Can you please once more explain the difference between both the files? I'm actually a bit confused because I
Okay.
didn't use much of file function during
Yeah, so
CS2.
actually, yeah, there is not much of difference, but I will just, for clarification, write it once again. And okay, this phi, sometimes people also write it like this, is the PDF of normal 0, 1. And this phi, where you put these two, horizontal lines over, this is the PDF of normal 0, 1. So again, whenever you're talking about this, you're talking about something being less than something. And if you're talking about this, it is just something being equal to something.
So the tables that we have in the table booklet, those are
Yeah.
of the below phi, the bottom phi,
Yeah.
PDF one.
Yeah, because so again, you don't even have to look at these things here. If you look at all the table booklets, you will see a graph in the top corner of your page, and there will be a region shaded, and that is the probability that the table is showing to you. And again, yes, it is this phi.
So you are talking about the normal, the small phi, right? The PDF phi. When you say
Yes, yes.
phi of minus infinity.
So
Okay,
that
I
would
got
be 0,
confused
right?
between the two.
That will be 0. Why?
Because we are finding the probability at a certain point, and in continuous distribution it's 0.
Exactly, right? So in continuous distributions, we know that this really doesn't matter. So it's going to be 0. So even if I write, it equal to infinity or minus infinity, it's always going to be 0, as rightly mentioned here. And again, if I'm looking at phi of minus infinity, that will be, so again here you notice there's two underlines here. So you are looking at the probability that you will get a value which is lower than minus infinity. And again, that's just never really gonna happen, right? Because minus infinity is the least that it can take in theory. And that is why a probability that you will observe a number which is even lesser than minus infinity is just 0 outrightly. So you have a 0 there as well. And the next up we have phi of infinity, which is basically everything that lies under the curve. And we know the area under the curve as it is, always 1, because this is a well-defined PDF, and integration of all this over all the area is going to be 1. So we're looking at less than infinity, so everything below this till minus infinity from infinity. So yeah, there you have it, 1. Does anyone have any doubts with this? Can you guys still hear me?
Yes,
Yes.
ma'am, I can hear you.
Okay, yeah, good, good. Okay, so does anyone have any doubts in this?
No.
What about others?
No, ma'am.
No, ma'am.
Perfect. So let us try to do a sum which will involve, the same kind of calculation that we just did in the previous sum, but just a bit of another stuff as well. I mean, actually a bit different as well. So here we have a question which says that, claims from a particular portfolio are normally distributed. So again, let us just, try to write it in terms of not words, but math. Mean 800. And I have a standard deviation of 100. So again, I write 100 here. Is this how I should write it?
It should be 100 square.
Exactly right. So again, we are given the standard deviation, not the variance. So yes, we have to be mindful of such things as well. So we are given excess of loss arrangement with the retention limit of 860. So we have M equal to 860. And what we are asked to do is now, we have to calculate the insurer's mean claim payment, net of reinsurance. So remember in the previous question that we did on the board was about reinsurance claim, right? And this is about the insurer's mean claim. So how do you guys think I should go about solving for this? So let me just write, expectation of Y is what we're trying to figure out. Anyone?
Integration 0 to 860 x f of x dx.
And?
Plus 860 to infinity. Integration 860 to infinity m f of x.
And what is my M? 860?
860.
And what should I write here?
F of x dx.
Perfect. And I guess let us just, ignore all of this for now and try to go through and see how they solve that. So I think this is the only step that we now need to know. And the rest of it is just, using formulas and everything else. So let's just go through the solution, I guess, because there's nothing really much more to it, except a couple of things. Okay, so maybe let's say even before we start, I want you all to, have page number 161 in front of you. So if you now see page number 161, we have two columns basically. We have a x and we have a corresponding phi of x, right? For everything. So now if I tell you guys to give me the value of phi of 6, what do you guys think it will be?
Is it 1?
What do others think? I want to answer from everyone. And where? What do you think? Yes, Vanshita?
No, I agree with Neil.
Okay, thank you, Savri.
Even I think it would be 1.
Okay, thank you, Vanshita. What about Isha and Anvaya? What do you guys think?
Ma'am, I don't have that booklet yet.
You don't have that booklet yet. Okay, so let me send you. Okay, so Isha, have you taken the CS1 exam?
Yeah.
So, okay, I'll just upload a PDF of this table booklet as well.
Yeah. Thank you.
So I'm sending you a picture. And again, I'm not sure, if this WhatsApp group is going to be active after today. So yeah, I have this. So now can you tell me what do you think? But you have, I mean, do you know
sorry,
how
you
to
were
look at the
talking
table
about
book?
this one. I thought you were talking about the main book.
No. The table booklet, yeah. I was talking about the table
Sorry.
booklet. That is why I was wondering, I was like, maybe you shifted homes or something else, or you left it somewhere else. But yeah, it's fine. So again, I have actually uploaded some material on the Google Class. Actually, I have only uploaded the
Ma'am,
PDF
can
of
you
our
repeat the page number, please?
161.
Thank you.
Anvaya, what do you think? Are you there, Anvaya, or not?
Yes, ma'am, I'm there. I'm just
Okay.
trying to.
Yes, ma'am, it will be 1.
Okay.
Ma'am, how did they figure out? I mean, how is it 1?
So can anyone explain? Can you say, Isha, why do you think it should be 1?
It will be 1 because as compared to these numbers, 6 is almost like infinity. So we have continuously, like even like right from 4.2, we have 0.999. Or we can also say that it is 0.999 itself, but we'll almost equate it to 1, right?
Okay, so if I go by what Isha is saying, we actually have 0.999 from 3.09 precisely. So again, till 4.40, we do have 0.999. And only the 4th and the 5th decimal point is altering, right? So, I mean, you guys aren't wrong when you say that it should be equal to 1, but it's just the terminology. So, okay, if I write equal to here, I don't know the answer because I just don't know its exact value. But what I can maybe write is exactly right. I can maybe approximate it to 1. So again, this is what oops, no, what happened? But yeah, this is what one needs to be mindful of. Again, I mean, I'm just being much more pedantic here and I shouldn't be. And I'm not even sure if your marks will be cut by the examiner if you by mistake, write equal to instead of this. But we just have to be precise in our thinking as well. So we don't know the actual value anytime until unless we have it in the computer. But we do know that we can approximate it to 1 for the purposes that we are concerned with. Because there will be other purposes where even, a decimal would matter and change everything. But yeah, again, we just don't care a lot about that. At least we aren't rocket scientists, where the mistakes could be huge. But again, it could either, lead to. So I actually, we'll come to the chapter copula where this was precisely the thought by people when they started using a particular formula and ignored the assumptions underlying it. And we all saw the 2007 financial crisis. There was only one formula behind all of that crash. And again, I think I don't know how much of you guys are into movies or something, but there's a movie known as Margin Call, which is all about that. So if anyone's interested, I mean, I know people who here would even want to be investment banker or something. So yeah, you should definitely watch that movie. I think you would definitely love it. So yeah, coming back to our question.
What
Okay,
year is
so
it
we
from?
have the movie. If you even ask me what actor is in the movie, I don't know. I only know the name of the movie and the story of the
Margin Call.
Forget. Yeah, it's Margin Call. So just, Margin Call. I mean, from what I know, it's on the Netflix. So yeah, I'm not endorsing anything else. But you can watch it on anywhere else as well, I guess. I don't know. Yeah. So yeah, I guess so. I'm actually a very forgetful person, whenever it comes to any other thing than what is interesting to me. So I just remember the plot of it and not even the actors. But yeah, anyways, coming to the point. What we have here is now we have figured out something that we are going to be required down the line. So yeah, let us try. So we have this integral right here. We have expectation of y equal to this first part and this second part. So again, let us just try to do the first part right here. We have 860 times the probability that my x will be greater than 860. So what can I do here? I'll have 860 as it is, and this will just be 1 minus the probability that my x will be less than 860. And again, I just standardized it. And there we are. So we have phi of 0.6. And if you go to your table booklet and if you have a look at phi of 0.6, you would see that this is the answer right there. So again, I guess now everyone has the table booklet. So yeah, this is the value that you will get, and that is the answer right there. So for the next integral, I guess you might have guessed, we have to use the truncated mean formula because we have from 0 till 860. So we have a 0 here, but not an infinity there. So again, what you do is remember the mean here, the sigma here. So 800 here, minus 100 here. And then the CDFs first, the PDFs next, and a minus in between. And that's it. So you have to figure out these numbers and then just figure out the values of these numbers from the PDF of from these table booklets. So phi of 0.6, we know. Phi of minus 8. Okay, so we don't have minus numbers in there. In the table booklet, we don't have even minus 1. Leave apart minus 8. So again, we are just going to use our normal symmetric nature of normal, because if we have a 8 here and if we have a minus 8 there, and what we care about is, let's say phi of minus 8, which is this area, because our normal distribution is symmetric in nature, we know that this half, if reflected upon this half, would exactly lay the same crease right here. So if I figure out this area, or if I figure out this area, it's exactly going to be the same. So what I do is, I figure out this area instead. And what I will get is everything minus what is below 8, right? So 1 minus phi of 8. And that will be our phi of minus 8. And that is what we have here. And again, phi of 8 can be approximated as 1. So you notice the change in sign here. So we know that this is approximately 1, and 1 minus 1 is 0. So that is how you get 0 over there. Is this clear to everyone?
Yes, ma'am.
Perfect. And I guess next up, yeah, we just, so again, here we have the PDFs. So what's stopping you from just substituting it directly into the PDF? Nothing. So we go on and we do that and we get some values. Again, here we have an approximation, but yeah, we just do it in the calculator and you'll get the values. So that's it. So again, you know, you all just add these up here. Again, notice the approximation sign here, and we have 783.13 as the expected claims for the insurer in this case. Again, net of reinsurance. So yeah, that's how you solve it, and that's it basically. So this chapter is nothing but writing this very first equation here. That's it. Because after that, it's just, you know, either applying the formula or just solving this stuff, which is simple math. And if it's not simple right now, don't worry. You will get used to it after you solve 1 or 2 sums. And it's just a matter of practice, I would say. Okay. So the same thing they have done with the log normal distribution as well. But there is some peculiarity here that I see in the formula, except than that was there in the normal distributions. So, okay, here my x follows log normal distribution. And again, we have to be mindful that, you know, our normal distribution takes, basically the domain of my normal distribution takes values from minus infinity till infinity. But for my x here, which follows log normal, we know that it can only be 0 till infinity, right? Because log of negative number does not exist. Log values are only defined for positive numbers and 0. Is it defined for 0? Anyone? What is the value of log of 0?
Not defined.
Not defined, right? Okay, so it is only defined for positive numbers because it just goes down. I mean, it has a shape like this. So yeah, that's it. Again, we have this formula and they have some derivation which I'm just going to skip through because it is easier, if not any trickier than the normal one. So yeah, because you only have to do substitution once and you get the answer. So, okay. But again, I want you all to, see your table booklet, maybe, and go to page number 14 and tell me, do you see any striking similarities from what is there in the description of normal distribution and what we have here? Do we have any similarities?
Ma'am, the first part is the arc moment.
Is it the earth movement?
In this case, the Cape moment, right?
Yeah, exactly.
Yeah,
Is it the Cape
yeah.
moment, right? Yeah. So that's it again. So you see that, this is again the expectation. So before, in the normal case, we had mu up there with the CDFs of U prime and L prime. And now what we have is the mean of the log normal distribution with the CDF of UK and LK. And the way we are defining UK and LK is just a bit different from the way we did prior to it. So again, if you go through its derivation, you will get to know why do we define UK and LK the way we have. But again, I think sometimes it's even a waste to open a table booklet and look up a formula where if you can get the intuition of why it is the way it is, you don't even need to open a table booklet for it. I mean, not exactly right now, but after you have practiced a couple of sums, I would say that will happen. Okay, so let us now try to solve a question which is exactly based on these concepts that we just studied. Okay, so I want you all to either take a picture or the screenshot of this question. Yeah, this is the question that we are going to solve right now. Yeah, I guess I'm back in there. Okay, so what I'm gonna do now is just, summarize the question. Did anyone take a picture of the question? Anyone? No answer is coming in? Okay, so we have our treaty 1. Let's just say it as T1, okay? So the treaty 1 states that the proportional reinsurance is in place with a retained proportion of 0.75. So basically I'm just defining my C as 0.75 in this case. And if I have treaty 2, what does treaty 2 say? Anyone? What should I write the summary of my treaty 2 as?
M is equal to 25.
Exactly. Perfect. So again, we are given that the claims, they follow log normal distribution with mu 8.5 and sigma square as 0.64. So again, these aren't the mean and variance of x. These are just, the parameters of log normal distribution. And that's it. So we are supposed to figure out the insurer's expected net claim payments in some cases. So again, we have to figure out expectation of y. Okay. So let us say our first case is without either of the treaties. So what do you guys think I should be doing? So let's say if there is not even treaty 1 and not even treaty 2 in place, what will happen to the expected payments is that the insurer will have to meet.
It will be expected value of x only. Right?
It will be expected value of x only, exactly. And what can I write that as? What is my expectation of x here?
E raised to 8.5 plus half is 0.64.
Does everyone else agree with what I have just written on the board or what Mihir just said?
Yes.
Everyone else?
Yes, ma'am.
So again, I guess these do matter, I guess. So again, remember if you're at mean expectation, and because we're looking at claims and they do come in pounds, so we have a pound symbol here. So yeah, that's there. Just for the sake of completeness. And now let's see the second case. So in second case, they are asking us what happens if we have treaty 1. So let us say now if we have treaty 1, what will happen? Anyone?
It will be 0.75 into expected value of x, right? So 0.75 into the current answer.
Exactly. Does everyone agree with what Isha just said?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay. This is easy, right? Not really that tough yet. Okay, so let us see what happens in the next case when we have treaty 2 in the picture. So in third case, we have treaty 2. Now let's see what happens.
And we have to completely ignore the decimals.
I don't know. I think you can ignore the decimals because neither I calculated this. I'm just copying this from the textbook.
Okay.
I mean, I don't even have a calculator here.
And I think it's in pounds, so I think we'll have to take the whole figure.
Yeah, I think, yeah, it's fine. So again, what should I be doing now? I want to figure out the mean claim payment from my insurance company if there is a retention limit of 25,000 in place with the reinsurance company.
Ma'am, it will be integration of 0 to 25,000, integration of from 0 to 25,000 x into f of x dx plus 25,000 into 25,000 integration of 25,000 to infinity f of x dx.
Exactly. So again, I guess, it's easier if we can just, directly go on to the integration step, but it's always convenient to write the distribution of y first. So as for us to, see what's happening. So if I were to write my y, I'll write my x less than or equal to 25,000, and I'll have my other case as x greater than 25,000, and in this case I'll just be paying x, and in this case I'll just be paying 25,000, right? And again, instead of writing, let me just write expectation of y as Vanshita just made it out. So I'll have 0 till 25,000 and x f of x dx. And instead of writing integral and then, doing, I think it's just easier. Again, I'm skipping steps here, but you can choose to write this if you want to. But I'm just writing it like this here. Does this make sense?
Yes.
Okay, and now what should I do? So I know how to figure this out, right? And I guess you guys do know how to figure this out as well. So do you guys want this as the homework? I would say, because I think, I think, yeah. So let me just give this as a homework and we can do something else in the class. Or do you guys want to solve it now as well? Now itself.
Yeah, we will try.
You will try this at home? Perfect. Okay, yeah, that's good. So I think what we can now do is we can start off with something else. So let me just ask you guys a quick question. Just give me a moment. Okay. So again, let us try to do something else as well. So we figured out the means of everything, and now let us try to figure out the variance of each and every case. What happens to the variance, okay? So again, we'll try to figure out the variance of y. What do you guys think will happen in the first case? How can I write my variance of y in the first case? Basically, if there is no treaty, what will be my variance of y?
There is direct formula in the table.
Exactly, direct formula from the table booklet, and here I'll just have 0.75 square times the variance of x, right? And again, what will you do here? Instead of x here and m here, you will have x square and m square here, right? And rest everything will just be the same. So again, take all of this sum as the homework, and I would say try to derive everything from the scratch. And yeah, let me just write here. Diwali time, right? Have you guys started preparations for Diwali already? Has anyone started collecting patakas? Or like, do you not indulge in patakas?
Stop bursting them.
Let's stop first and then. That's good. That's good. I mean, yeah, we do hear a lot about, air pollution these days. And I guess, yeah, it's only good to not burst crackers. But yeah, that's my personal philosophy. And yeah, we can choose basically what we want to do, but try to avoid it if you can. Okay. So again, can I ask you guys a question? I mean, let us say if I have, a certain claim amount this year, and I have analyzed all of my claims from my past, and I have reached a certain conclusion that this is what I would have expected my claim to be this year. But would it be the same? I mean, what do you guys think the amount of claims, what will happen to the amount of claims as and when you move forward in the years? Anything that happens in the economy that might affect the claims equally, each and every claim, not any particular claim, but yeah, in general. Basically, so everything that we have yet studied, there is an implicit assumption that we made, We are assuming that the claim distribution will stay the same throughout. So what we are doing is we analyze the claims from the past and we see which distribution fits it the best, and we foresee that that will be the same distribution which will fit the best the claims in coming year to come, right? So is this always true, or does something else play a role in the real life as well with the amount of the claims that we are looking at? So as again, has anyone had a look at, the insurance policies taken by your grandparents or your parents when they were a child or something of that age? What was the premium that these guys were paying? Does anyone have a clue? Any amount that they can think of would have been the premium in those days. I mean, on an average. I mean, it differs for the policies and everything else, but yeah, just on an average.
Ma'am, if we're talking about the very long term, like over a period of 30, 50
Decade.
years, then we can say that inflation plays a part.
Yes, inflation does play a part. And can you explain it a bit? How does it play a part?
Basically, the value of the money goes on changing. So the same thing that, our parents or grandparents could purchase in 5 rupees, we need to pay much more for that right now. So similarly, we can say the same thing about premiums as well.
Very well explained, Isha. So again, we can see the same things about the premium that we are paying. And we can also see the same thing about the claims that we would be making. So the amount of claims that you make might also be affected by the inflation that you have in the economy. And again, the way you measure the inflation differs a lot. So some people will, prefer to use the CPI, which has a certain basket of goods that they consider and certain things that they do ignore. And some people might consider something else. So again, that is something of your personal liking. But again, for our purposes, we don't actually, I mean, the book doesn't really lay out any of these practical inflation measures. Again, I think even if it would have, this is from the UK, so they wouldn't be considering what happens in the India. But again, I think the economic standards are, the same across all the countries as well. So let us try to see what happens if there is an inflation next year of some amount. So again, how is the inflation represented? I mean, do we have a particular amount for inflation, or do we have something else for inflation? How do we say कि inflation कितना हो रहा है? Is it a ratio? Does it have a unit?
Percentage.
It is a percentage, right? And again, if I say that the inflation is, so again, I think there is a bit of terminology involved. So some say that the inflation rate is 8%, and some say that the inflation factor is so and so. So do you guys know the difference between rate and factor?
Is factor expressed with respect to the base year or something? So if it is 8%, then maybe it can be written as 108 upon 100, with 100 referring to the base year.
So I mean, I think not exactly that, I would say, but you are, I mean, no, I wouldn't actually say that's true.
Ma'am, rate is the percentage growth over, say, 12 months.
Okay. And percentage growth. So what exactly do you mean? Factor would be if rate is a percentage of growth. Yeah, I guess I'm back in the meeting. Okay. So the difference between rate and a factor is actually, not much of I mean, it actually just matters for us in the way they ask us questions sometimes. So if they say that, inflation rate is 8%, then it means that, we just write it as 8%. And if I write that my factor is something so and so, then it will be 1 plus 8%. So it will be something like 1.08. So exactly, I think what someone else said, right? I guess it was Isha. Was that you, Isha? You said it would be 100
Yes, ma'am.
plus 8 upon 100. So yeah,
Yes.
exactly that. I think I said it was wrong or something.
Yeah.
Yeah, so that's actually not wrong. This is exactly what it is. So yeah. So this is how we write a factor, and rate is generally denoted by R. I don't know what is factor denoted by, but you can just write it as 1 plus R. And R is in terms of percentages almost always. So that's just a subtle difference. And again, so again, whenever I'm talking about the claim amount that is incurred by either the insurer or the reinsurer, now we have to see what happens if we have a projected rate of inflation, some number. So let us say we have a projected rate of inflation as K. So what will happen to the claim amounts if my inflation is projected to be, of K? So let me show you guys how does things alter if we have inflation and Does it make our calculations a bit simpler? I mean, we don't necessarily think it's gonna make our calculations simpler, but yeah, let's see what happens. Just okay. So if I'm talking about inflation, let us start with what will happen with the insurance company. Okay. So we have our usual claim amount X. So this is our claim amount and K is the inflation. And again, when I'm talking about this K, what I'm writing here matters a lot. So this is my inflation factor here. Okay. So let us say if I say that, I have a claim amount X and it is projected to grow at the rate of 8%. Then how should I write my new value of X for the next year? So let's say this is my year 1 and this is my year 0. I have a X here and I'm saying that my R is 8%. So what will be my value for year 1? Anyone for this X here?
1.08 times X, right?
You say X times 1.08, right? And what is this 1.08? Just 1 plus R. So this is my factors, right? So now if I'm saying that my X is projected to, grow by 8% or that there is to be an inflation factor of K, then I can write that the next year for which I'm trying to figure out the distribution of Y here will have instead of X, KX here, right? Does this make sense? Because in the actual scenario where the inflation factor, was just 1, where the rate was just 0, and it would still have been the same. I know I would have just written the X here, but now I say that it's going to be, so this is basically my K here, 1 plus R, which is the factor, inflation factor here. So I have my KX here. Does this make sense?
Yes.
And again, so I'm assuming that my retention limit, it stays the same. It is not inflated by the inflation in the economy or something. It stays the same. So what's going to happen here? What should I write here as the condition? What will be my condition now? Anyone would want to guess?
Ma'am, can you repeat your question?
Okay, so my question is that, usually what we have in normal scenarios is xm for x less than or equal to m and for x greater than m. So I'm wondering, what should I write here now that I have this inflation going on?
Ma'am, why will the condition change?
Why will the condition change? Okay, that's a
Because the
good question.
retention,
Because yes, go on. Why do you think the condition should not change?
ma'am, because like if the claim amount is changing, they have to even eventually change the retention level according to inflation. So if the inflation rate is same,
So I'm assuming that my retention level is still n. It doesn't change.
Okay, then it will change. I thought even the retention level will be changing according to the inflation.
No, so I'm not planning to change the retention level. So what will happen if I don't change the retention level?
Will it be kx less than m?
And why do you think so?
And the claim, like in the earlier when there was inflation, we were considering the claim amount is less than the retention level, and now the claim amount is becoming kx. So
Right? So it will just be kx less than m. What do other people think? Do you guys agree with what I have just written here?
Yes, ma'am.
So does it make intuitive sense? So again, instead of x, see, in the actual scenario, we know if there was no inflation in the economy, then it would have been x here and x less than m here. But now, if our claims are projected to grow at the rate of k minus, just with the factor of k, then what's going to happen to my claims? My claims will also get multiplied by k. So now instead of x, I have kx everywhere. So the claims which will be incurred by my company, if I'm the insurance company, will be of kx amount, right? And now I would be checking if that kx amount, is it less than or greater than m, to figure out how much I have to pay or incur. So the next condition would obviously be kx greater than or equal to m. And what should I write here now? Anyone?
K into M.
K into m. And why do you think I should write k into m here?
Because that should also be inflation adjusted.
Okay. How many of you guys agree with what Isha just said?
if we are not changing retention level, then it will be just m, right?
Even I feel what Sauri says.
So can you guys convince Isha why do you think it should be m? Come on, Anvaya. Why do you think it should be m?
I feel because we are not changing the retention level, we won't apply inflation to it here as well.
Isha, what do you think about this explanation?
I think it's valid.
You think it makes sense, right? Because we aren't really changing our retention level and the inflation does not affect it. And again, the very fact that we have written m here, so we know that if it is less than m, you pay kx, and if it is greater than or equal to m, you just pay m, because the retention limit stays as it is. It does not alter at all with the going on inflation. Okay, so that is how it will happen if you have, excess of loss in place. Okay, so again, if now I were to, again, rewrite basically this distribution, I can rewrite it as, this is again taking the value kx, and this is again taking the value m. But because we don't know anything about the distribution of kx, and we know directly about the distribution of x, what I can write this conditions as is this. Does everyone agree? Does this make sense?
Yes, ma'am. But why did we do that?
Why did we do that? That's a good question. I mean, it's not necessary. I wouldn't say it's necessary. So let us ignore this for a while, okay? Let us just assume that we haven't yet done this. And now we try to figure out the expectation of y. So what do you guys think I should write? So again, ignore this and we just have this. And now let us try to write the expectation of y. What do you guys think I should be writing?
Integration 0 to m kx f of kx dkx.
It does
Plus,
seem a bit odd, right? I mean, we
yes,
have this dkx and everything. So we just ignore all of this and we write it in such a manner so that we have x's value here. And what we can essentially do is we can write this expectation of y as easily 0 till m upon k here instead of just m, and kx f of x dx plus m as it is integration of m upon k till infinity and f of x dx. Does this make sense now?
Yes, ma'am.
And this is nothing but the probability that my x takes a value greater than m upon k. Okay, so now let me try to share our PDF again, and we'll try to have a look at an example where we have an exponential distribution for the claims. Yeah. So we have this question, and let us try to solve through this. So have a quick read at this question, everyone, and just tell me what should be the summary of the question, and then we'll proceed to solving of that question. Is everyone there? Can you all see the question? This?
Yes, ma'am, we can.
Yeah. So what is the question asking me to do?
Expected value of y in the first place.
All right. And what could that be?
Alpha by lambda.
Exactly. And why do you think it should be alpha by lambda?
Ma'am, because it's proportional reinsurance, so the expected value of y will be the value of proportion into expected value of x. The value is given as alpha, so alpha into expected value of x, and expected value of x is 1 by lambda.
Exactly. Right. That was absolutely correct. Good. And what about the second part? So now we have an inflation factor of k. What will happen now?
It will be alpha k upon lambda.
Yes. What will it be?
Alpha k upon lambda.
Why do you think so?
Because in the next year, inflation factor k is multiplied to the claim amount x. So therefore, it will be alpha expected value of kx, and k will come on outside because it is a constant, and then again expected value of x.
Exactly right. Does everyone agree with what Mihir just said?
Yes.
Yes, ma'am.
Yes,
Does
ma'am.
anyone have any doubts with what I have written on the board itself?
No, ma'am.
Okay. So yeah, I would say that's it. Again, so yeah, I guess that's it. And that is how you would solve this question. It was pretty straightforward, I would say. And we did this. Oh yeah, this is very important. So, okay, we should really try to figure out the mean amount in this case. If we have exponential with lambda x, and if we aren't looking at the proportional case, but at the excess of loss case, and this is, really not straightforward. So let us try to figure out this expectation if we have x following exponential of lambda. So do you guys want to try solving this integral? And also, are you guys aware of integration by parts?
Yes, ma'am.
Oh, that's really nice. So will you help me to try this sum? Let us try to see what's happening here, okay? So again, to start off with, we did write this formula of expectation of x, expectation of y previously, and we are aware that this goes now from 0 to m by k. So 0 to m by k, kx is the new claim amount and multiplied by its chance of occurring and dx. Plus I have m times the probability that my x takes a value greater than m upon k. So that's it. And now if I say that my x follows exponential with lambda, I can easily substitute my values of f of x here, which is lambda times e raised to minus lambda x. And this will be as it is. So if I were to solve for this part, I know it will just, be m times 1 minus the probability that my x takes a value less than m upon k. And I can easily substitute the PDF of m upon k here and get the answer for this part. So let us ignore this part for now and try to solve for the first part here. Yeah. So do you guys know about ILATE? Have you guys heard of this?
Yes, ma'am.
Can you tell me what these are?
I is for inverse, L is for logarithm, A is for algebraic, T is for trigonometric, and E is for exponential.
Exactly. So has everyone else heard of this before?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, Vanshika. Okay, so I guess that's good that we all know what ILATE is. So, okay, but again, even before we think of ILATE, we have to, see something else on what that is. Anyone? So again, let me just write the integral that we have at hand here. So we have integration from 0 to m by k, and we have k. Let's just put lambda outside and k also outside, nothing to do with us. And we have x e raised to minus lambda x here, dx. Okay. So how do you guys think I should go about, using the integration by parts formula? Okay, so to start off with, who can tell me the formula for integration by parts?
For this particular thing or u and v?
I mean, anything.
So if we take in u and v form, so it will be u into integral of v minus v, minus integral of u d by dx, du, no wait, dx by du, or
It will be du, I mean u prime. If I write u prime, that's just denotes the derivative of u.
U dash,
right?
Yeah.
Yeah.
Minus again, into integral of v, and yeah, we are integrating this with respect, like with the limits of what?
Yeah, okay.
It will be du,
Should
right? Or dv.
What do you think it will be? So for this, we will have dv first, and then we'll also have du.
Okay.
Does this make sense?
Yes.
Because we have two integrals, right? So yeah. So let us try to solve for this now. Now that we also know the formula. So what do you guys think I should be doing next?
x into integration of e raised to minus lambda x.
X into integration of e raised to minus lambda x. So again, my u here is x, and I have considered my v as e raised to minus lambda x. Why? Because I'm kind of using my Eilert rule. So a comes first and then comes e, and this is algebraic and this is exponential. Perfect. And next, what should I do?
Minus integration of, so the derivative of u, that is x, would be 1.
Yes. And then what should I write?
Integration of e raised to minus lambda x. Yeah.
Dx.
And again dx.
Right? Okay. And again, we have this k lambda here, which I kind of forgot to write here. So everything gets multiplied by k lambda. Okay, what should I be doing next?
Solving the integration for e raised to minus lambda x.
Wait, what did you just say?
Solving the integration for e raised to minus lambda x.
So this will be what? What should I write next?
E raised to minus lambda x upon minus lambda.
Exactly. And this would go from
0 to n by k.
right? It would go from 0 to m by k. And again, what I have to remember is I have to take, let me just erase this. Yeah. So yeah, we'll have everything from, so basically what I just did was I would have this going from 0 to m by k, and then again all of this going from 0 to m by k. So I just made it in one. Oops. What all have I been erasing? I guess that's it. Does this make sense? What should I be doing next?
The same, solving the integration.
Okay, so can you help me with it? So I'll just keep this integral as it is, and what should be my answer for this integral?
E raised to minus lambda x upon minus lambda.
It's the same, right? So I'll have again minus lambda, and again I have dx here, right? With some integration, and so what will I get here? So let's just put this k lambda inside everywhere. So my lambda here and my lambda here will get cancelled because this is just a constant. So it won't anyways, depend on anything else. Right? So what will I get here? K, and I'll have x e raised to minus lambda x, and this lambda and that lambda would get cancelled. So minus will come outside. I'm just keeping it outside for now. 0 till m by k. Okay. And again here for the limits, we have to take k and lambda inside. So again, this lambda and that lambda would cancel each other out. this minus and this minus would become a plus, and this k would be as it is here, k. And we have e raised to minus lambda x dx. Does this make sense?
Yes.
And now what should we be doing? So basically minus k, and again you can easily, substitute in this. I'm not going to substitute it. So it goes from 0 to m by k plus k, and you again integrate this thing. So you have e raised to minus lambda x upon minus lambda. And again here, because it's just k, and with the integral 0 to m by k. Does this make sense? Right? So that's it. And I guess we do have, our answer to this, and you will just have to substitute these values inside. And that's it. Let me see if I can maybe. Oh, no. So yeah, I guess. So was that clear to everyone?
Yes, ma'am.
I think it just needs a bit of a practice, and it's really not that difficult, just figuring out what your U should be and what your V should be. That's it. And you have to use eyelet for it. So that's done. And yeah. So I guess we got this thing, and then we got this thing. We even solved for this integral. And if you do the cancellation and everything, so here if you try to solve, you get something like this, and this term and the term here actually gets cancelled out. So again, even before substituting for the values, just try to see what happens and if there are any cancellations to be made, and then basically you will get this answer. So again, I want you all to, do this whole derivation from scratch once again, and maybe try this at your home and give me the final answer as the homework. Can this be expected from you all? I mean, anytime till the next week, you can submit it. Nothing to worry about that. So yeah, and again, I would say, this paragraph is very important. Can someone read this paragraph out and say what does this say, basically, in your own words? Read this paragraph. This. Who is gonna read? Anyone can read. Anyone? Who would like to volunteer, or will I have to call out a name? Anvaya, would you like to read this? Is everyone there? I just wanted to read it. Vanshita, can you read it for me?
Okay. The insurer's mean claim amount will inflate by less than K. We can see this by considering different sizes of claim. From the insurer's point of view, the amount it has to pay out on small claims, those that are nowhere near the retention limit, will increase by K. However, the amount paid on claims that were already above the limit will not increase at all, and the amount paid on claims that didn't reach the limit before but now do will increase, but by less than K.
Okay, so if you remember what happened in the proportional case, when we derived this, so when we derived this expectation of Y, in the case of proportional reinsurance, remember our answer to the first case was alpha upon lambda. And then if we take inflation into account, the expectation was alpha times K upon lambda, right? So basically the new mean after inflation was just K times the mean that was there if there was no inflation into account. But if we have a non-proportional kind of a treaty, what happens is, if you again, let me just write the distribution again for Y. What do we have here is Kx less than M, and here we want Kx greater than or equal to M and M here. So again, now if we are trying to figure out the insurer's mean claim amount, in the case of excess of loss reinsurance, compared to the case where there was no inflation, what's going to happen is that the claim amount will increase. See, the claim amount will increase for sure, but it says that, it will increase by less than K. And what it means is that it is not directly, equal to, K times multiplying the mean claim amount that was there before. And now we have to see why is that the case. I think this is a very good intuitive explanation. And this is a very good exercise to even try to think about why should the mean claim amount for the reinsurer in case of excess of loss, for the insurer in case of excess of loss reinsurance treaty should be inflated by less than K compared to, in the proportional case where it gets inflated directly by K. Would anyone want to try to guess as to why is this the case before I try to explain? Anyone would like to try? Would anyone want to have a guess as to why would that be the case?
Ma'am, I'm not sure how to explain, but I'll just say what I can, like how I can explain. I'll just try it.
Yeah,
So, ma'am,
go
when the inflation wasn't there, if the amount was X and basically after the inflation, the amount increases by some K amount, and if that K amount if that total amount goes up, goes beyond the retention level, so the insurer has to pay some amount, but it will be somewhat less than, not less than, but it has. Okay, I can't explain it. I maybe got the point, but I'm not able to explain it. Sorry.
No issues. Actually, don't worry about that. Anyone else would want to try? Savri, do let me know if you want to try again.
I think we can take a simple example. If the retention limit is some 10,000 and the claim amount after inflation is adjusted is like 15,000, but as the retention limit remains same, the insurance company will pay 10,000 only in case of inflation also, if the amount of claim is above the retention limit.
Okay, so first of all, Mihir, tell me one thing. Can this case even occur where my KX is 15,000 and my M is 10,000? So basically, my reinsurance company says that if there is any amount which exceeds 10,000, the rest of it will be paid by the reinsurance company. And only the amounts prior to 10,000 will be incurred by the insurance company. So if you write 15,000 here, basically lies, let's say it lies somewhere there, then we sort of know that, only the 10 will be paid by the insurance company, and the remaining 5, which is the difference between 15 and 10, which is the M here, will be incurred by the reinsurance company. So again, we have to respect the boundaries that we have set here. My KX should be less than M. So my KX, which is 15,000 here, cannot be, simultaneously here with M being 10,000.
Ma'am, I was trying to explain that point. However, the amount paid on the claims that were already above the limit will not increase at all.
Ignore. So, I mean, okay. I will explain to you guys what that line means. I mean, it is not exactly what you just tried to do here. But do you get why can't we write this 15,000 and 10,000?
Yes, ma'am. Yes, ma'am.
Okay. But anyways, good try. What about others? Would anyone else want to try? Think. So just, try to think what's happening from the first principles. Let us ignore everything else. Let us ignore even the numbers. Just let's forget about the numbers. So what we have is, अगर सादा केस रहता बिना इन्फ्लेशन वाला, तो हमारा जो कंडीशन रहता, it could have been y taking the value x for x less than m, right? Now we are saying कि economy में there is an inflation of factor k. So all the claims have increased by the factor of k, right? So जो हमारे पहले claims थे, and let us divide our claims into two things. The way they have explained it here. So we say that the claims which lie in this category are small claims, and the claims that lie in this category are large claims. Okay, so we have these two terminologies here. And again, we know that even the claims that are in this large category will be increased by a factor of k, right? They will be increased by a factor of k. So again, if I'm multiplying a smaller number by k, or if I'm multiplying a bigger number by k, the change, the absolute difference would be bigger in which case? So let's say if I multiply 30 by 2, or if I multiply 100 by 2, I have 60 minus 30 is just 30, and I have 200 minus 100 as 100, right? So whenever I'm considering the mean claim amount, I'm considering the absolute numbers, not the percentage difference, right? Or the multiplication or the division of anything. I'm considering a simple subtraction of it. Basically, कितने से मेरा amount बढ़ गया. So पहले अगर मुझे 30 पे करना था, अभी मुझे 60 पे करना पड़ रहा है. If I'm the insurance company, and let's say if my retention limit is 50, and then I incur a claim of 100, right? तो अभी जो उसका claim amount हो जाएगा exactly after M. So if my M is 50, now the actual claim amount multiplied by k equal to 2 will be what? 200. And if I subtract 50 from it, what is left is 150, right? Which is a very big amount. So for me as an insurance company, अगर inflation नहीं रहता, तो amount कितना था? 50, and 50 it was distributed 50% for the insurance company and 50% for the reinsurance company, right? But now if it's 200, only 50 is paid by the insurance company and 150 of it is paid by the reinsurance company. So now it is in a way 1:3 का ratio हो गया, right? So you see how the distribution completely varied. So now the mean claim amount for the insurance company is kind of less. So it will be inflated by less than k, because for the claims which go above and beyond M, उनके लिए तो कोई change हो ही नहीं रहा है, right? The claim amounts stay as it is. For the second category, when I'm talking about these claims, for the insurance company, the claim amount is still M, right? But if I'm, let's say, talking about the reinsurance company, it changes a lot. Because let's say अगर हमारा 100 का था, let's say my X is 100, and if my K is 2, and my M is 50, and if there is no inflation, then insurance company was paying 50, and my reinsurance company was paying 50. And if there is an inflation, I am still paying the 50. But because now my claim value is X times K, which is 200, and the rest of it is paid by the reinsurance company, it becomes 150 suddenly, right? So what's happening is only one category of the insurance company's mean claim amount will be altering by a factor of K itself, and the rest, instead of altering by K, it is just staying where it was. They still have to only pay M amount of it, neither more nor less. So if you take the mean, basically if you take the total of both of these, it is in a way inflating by less than K. Can you guys see it now? Does it make some sense?
Yes, ma'am.
What about others?
Yes, ma'am.
Good, right? So that is what they are trying to say, I guess, let me just try to read it again. So we can see this by considering different sizes of claim. Forget about that. From the insurer's point of view, which is why the amount it has to pay out on small claims will increase by K. So small claims has increased by K. However, the amount paid on the claims that were already above the limit will not increase at all. We saw this, right? Because पहले भी 50 था, अभी भी 50 है, inflation हो चाहे ना हो, same amount. So it will not increase at all. Right, that's it. That is exactly what they are saying. So again, if there are two parties and if the mean claim amount for one party is inflating by less than K, then I think it's only, complementing that the reinsurer's mean claim amount will increase by a factor of more than K. Does this kind of make sense? If this is not clear, do ask me again and I'll be more than happy to explain all of it again. Does it make sense? Do you guys see why would that be the case? I want either a yes or a no from everyone. I mean, if you have understood it, yes.
Yes, ma'am.
If not, no.
Yes,
Please
ma'am.
do not hesitate. Thank you. I've got 2 yeses.
Yes, ma'am.
Thank you, Mihir. What about others?
Yes, ma'am.
Thank you. Isha, did you understand?
Yeah, I said yes, ma'am.
We have already said. Who did I miss?
I
Okay.
So I
Did
actually
you
couldn't pay attention for the whole thing. So I'll watch it again, the video lecture, and if I have any problem, then I'll.
Okay. Yeah. Please do. Okay. Please do ask me or in the group or your fellow classmates about it. And because I think it's an important point, but again, I think it's fairly simple once you get the intuition of it. And I think that's it for today. So again, here they are just talking about, what happens if we even link a retention limit, which is M, to inflation. So I hope, if anyone would like to try that case, I'd be very happy, to assist you along with it. And if you have any doubts, do let me know. And in the next lecture, we'll look at the estimation part of it. I mean, there's really not much left of this chapter as well. So I am stopping the share. Yeah. And